So we have one last key topic to talk about in terms of electric circuits and the quantities in them. We've done current, we've done voltage, next up is resistance. So let's talk about what resistance is. So resistance is just a measure of how hard it is to make a current go through a material. And the reason a material has resistance is because the electrons or the ions passing through it make collisions as they do so with the positive ions inside that material. So the vibrations of the ions is what can cause the electrons to have collisions. More vibrations, the harder it is to go through, or the closer packed the ions, the harder it is to go through. And all of that causes resistance. So the way that we calculate resistance is we can measure the potential difference and divide that by the current that's passing through the material. Now I've intentionally here written potential difference across a component divided by the current through the component, because I want to emphasize the fact that you need to think about the way you talk about these ideas. I have seen exam papers where students have been penalised for talking about the current across a device. If you're talking about the current being across it, it's showing an inherent misunderstanding of what current is. So make sure that you use these terms correctly. So basically that just simplifies into R equals V over I, where your resistance is in ohms, your potential difference is in volts, and your current is in amps. The more common form that you'll see is V equals IR. It's just rearranged, and obviously we can rearrange to I equals V over R. So we've now got another new unit. We've got the ohm, and the ohm is the resistance of a component when a potential difference of 1 volt is produced per amp of current. Pretty simple and straightforward. So how do we measure the resistance of a device, of a component, sorry? Well, first thing we need to do is build a circuit, and the one I would pick is one that looks like this. So I've got a variable resistor in here, so that I can vary the amount of resistance in the rest of my circuit, which will allow me to change the current and the voltage across my components, so I can take multiple readings. Instead of having the variable resistor, I could have a variable power supply instead, and that would work equally well. The method I'd say is measure the current through the resistor using the ammeter, measure the potential difference across the resistor using the voltmeter, calculate the resistance using R equals V over I. But rather than just calculating the resistance once, it would be better to take further sets of values of I and V by changing the setting on the variable resistor. And the way I'd find an average value for the resistance is by plotting a graph. And I would plot a graph of, it doesn't actually really matter which way you plot it, so let's say we'll plot a graph of V against I, because if I plot a graph of V against I, I've got V on the y-axis, I on the x-axis. The gradient of that line would be y over x, which would be my resistance, and that would give me a good average. The second method is, if you have one, just use an ohm meter. But you need to start thinking about this idea of how to perform practicals. Whenever we're thinking about practicals, you want to think about how am I going to take multiple readings, what are those readings I'm going to take, what will I record them with, what graph am I going to draw, and what is the gradient of that graph going to represent. These are often 6-mark questions on the exam, and if you think of those steps, that's how you'll get those 6 marks. Okay, so this leads us to Ohm's Law then. So Ohm's Law states that the potential difference across an ohmic conductor is proportional to the current through it, provided the physical conditions do not change. So basically, V equals IR. And in terms of a graph, that would look like a straight line. So for a component that obeys Ohm's Law, you'd get a straight line through the origin for a graph of voltage against current. And in this case, the gradient of the graph would be equal to the resistance of the conductor. And the physical conditions we often talk about are temperature. That's the big thing. If it gets hot, that is going to affect the resistance, because if I increase the temperature, I increase the way that those ions are vibrating, which makes it harder for the current, for those charges to get through. So if I want to investigate Ohm's Law, there are 2 circuits that I can use. So if I want to find out if a component does obey Ohm's Law, I'd use one of these 2 circuits. I can either use a variable resistor like this one here to control the amount of current or voltage that goes through it. Or I could use a potential divider control, which looks like this one. Now, we will talk about potential dividers later in the topic. The potential divider is better. And the reason it's better is because we can get a wider range of values. Looks a bit more complicated, but it is the better option. So you may need to be able to talk about that later on, but don't worry too much about it now. Just store that piece of information away until we talk about potential divider circuits. So if we do this for a circuit, wrong thing, don't want me in the middle, big and scary like that. If I do this for a wire or a resistor, and I get a set of values for voltage and current, what I would plot is its IV characteristic. And for this, we plot I on the y-axis and V on the x-axis. For a wire or just a fixed resistor, that would give me a straight line that goes right through the origin, which shows me that it would obey Ohm's law. Now, I have plotted here an IV graph, not V against I. So the gradient of this graph is actually 1 over the resistance. So that means a larger gradient means a smaller resistance. So just bear that in mind whenever you're talking about these graphs. And just get used to the idea. It will always be an IV characteristic. So you need to know 3 of these. Fixed resistor, a filament lamp. Filament lamp looks different because its resistance increases as the current does, and that's because it gets hotter. So what we end up with is a sort of S-shaped curve. So it still goes through the origin, but it curves at the top and the bottom. So that means it does not obey Ohm's law. I'm just going to very quickly talk about thermistors, because this is something I could throw in there. For these, as long as the temperature remains the same, the resistance will stay the same. But at different temperatures, they will have different gradients. So for here, I've got an example of one at a high temperature, so I've got a low resistance, and a low temperature, so I've got a high resistance. So as long as the temperature is the same, they do obey Ohm's law, same as a fixed resistor. Right, the third one that you very specifically need to know are diodes. So this could be an LED or just any sort of diode, and they look like this. So I get a practically zero current when the voltage is in the negative direction, and then I get this shape on the right hand side where I get nothing for a little while, then it starts to increase, and then it very sharply increases. So in the reverse direction, we have very high resistance. So typically you get a current that's below 1 microamp. And you can describe the resistance in this direction as being infinitely large, because in the exam they'll just tell you the current is 0. So that means that the resistance is infinite. In your forward direction, if the potential difference is below about 0.6 volts, it normally is, you'll find the resistance is high. Once you get past 0.6 volts, the resistance sharply decreases, which allows the current to go up very quickly. And there is this important feature, this 0.6 volts, where suddenly it changes. And this is what we call the turn-on voltage. This is the voltage where, if you have an LED, the LED starts to glow. They're often a little bit different for different diodes, so they can be in the range of anywhere from 0.6 to 1.5. So that's the point at which the LED starts to glow, and that's where you see the sharp change in the resistance. And it's just that we need a certain amount of voltage in there before we can get the current flowing. Okay, so that is it on resistance and Ohm's law. Remember, any questions? Ask when you see me.